Well, folks, today is Saturday morning. Yeah, we are going to do the fourth lab session. The topic today is classifiers. So we covered classifiers in the theory section on Thursday. So we will now bring it down to actual practice. Now, I would like to review what we learned in classifiers. And then I would like to also finish one more topic, one more type of classifier before we go into the labs. So we talked about the fact that in classification, you identify a class from a set of classes. Given certain attributes of the data, you say, well, this must be a cow or this must be a duck. And if it is small, feathery, and so forth, webbed feet, these are all features. Given the features, a classifier, a successful classifier should be able to say, well, this must be a duck. So that is classification. Now, when we do classification, machine learning is all probabilistic. There are no certainties here. So one of the intermediate steps is you produce a probability that it is a duck or a cow. When you produce such probabilities, it leaves a final task at hand. At what threshold would you put the cutoff and say, beyond this threshold of probability, it is a duck. So if the probability of a duck, whatever it is, the probability of a cow will be 1 minus the probability of the duck. You can arbitrarily pick one of them as the positive case. Let's say ducks. If duck is a positive case, then you say that if the probability of duck is 50% or greater, it must be a duck. That is one way of looking at it. And where you put the threshold, we talked about it. It depends on what the real life situation is. For example, if you're doing diagnostics for cancer and it's an early screening test, you want to make sure that even 10% probability or very low probability that there is a malignancy, you would flag the person as a positive case needing further investigation. Isn't it? You flag it. So you will end up with a lot of false positives, but that is a worthwhile price to pay, because if you get a false positive, the worst that would happen is the person would go through further tests and then it would turn out the person is quite healthy. On the other hand, if you miss a positive case, then time is the enemy. The untreated cancer can get to the higher stages where it is far more expensive, both in terms of medical care and in terms of human suffering, to bring the person back. So it all depends on the context, okay, where you put the threshold. Now, we also talked about the confusion matrix. The confusion matrix tells you, it basically says how many positives were identified as positives, how many negatives were identified as negatives. The diagonal are the correct answers. The off diagonals are mistakes. So for example, if a negative sample is marked as positive, this is your false positive. This is saying that a perfectly healthy person actually is cancerous, right, in a diagnostic tool. Likewise, a false negative is when somebody does have cancer, but you say no. Your classifier says no, the person is healthy. Now, we talked about accuracy and error rate. Two things that I left you to figure out were precision and recall. This was a homework. I don't know how many of you did that homework, but now I will, in a short while, I'll explain to you what those things are. I talked about another model diagnostic. It is called the receiver operator characteristic count. Its history predates the notions of machine learning and classifier. It has to do with the false positive rate and the true positive rate. Initially, it has its roots in signal processing, so forth, communication. And what we search for is the area under RC. A bad classifier, a random dummy classifier, would show a linear behavior. You increase false positive rate, you increase true positive rate, your false positive rate will go, because it's making random guesses. But a good classifier will be able to achieve a pretty high true positive rate at the expense of a very tiny false positive rate. Since machine learning algorithms are all probabilistic, we have to be cognizant of the fact that there'll always be an error rate. Remember, this is the same thing as the irreducible error we talked about in the case of regression. Irreducible errors, the errors that you can't get rid of, comes from the fact that there are many things you don't know. Your model hasn't accounted for that probably. If it did, the error rate would go down. And it also comes from instrumentation errors. So you can only make the area under ROC curve that good. Now, I talked about two interpretations of frequency, of probability. The frequentialist interpretation, which is based on number of trials. Probability in their definition is proportion. And then there is another definition, which is probability is the degree of belief. How much do you believe that something will happen? If I toss a coin, how strongly do you believe that it will come out heads rather than tails? Okay? How strongly do you believe that tomorrow it's not going to rain? Things like that. And it turns out that both of these probability definitions, they follow exactly the same arithmetic of probabilities. Okay? Now, which one you take in practical terms is a matter of, it is simply a matter of convenience. In many places, it is perfectly okay to go with the frequentialist definition. It gets the work done, though one would argue that the Bayesian definition is more nuanced, is more theoretically correct. We talked about, given probability, out of probability, we created a notion of surprise, or it is what I call surprise. The technical term would be the information content. How informative something is if it happens, but the probability is low. So if you know that the probability, there's a probability of no rain, of dry day, is close to 99%. Tomorrow it doesn't rain, or today it doesn't rain, you're not surprised. There is not much information if somebody comes running to you and says, hey, it didn't rain today. You'd say, what else would you expect? On the other hand, in the desert, the probability of rain would be, let's say, 1% or 0.1%. And somebody came running to you and said, oh, good, great. Did you know today it is raining? And now you would be very surprised, isn't it? So there's far more information content when an unlikely event happens. So surprise is the reciprocal, effectively reciprocal of the probability. With a log, you put a log there, and when you do that, it ensures that events of no surprise are zero. Their values are zero. The surprise values are zero. Where there is certainty, there is no surprise, and no surprise means zero. Surprise should evaluate to zero. So log 1/e, therefore, is a good measure of surprise. With that notion, actually, I just noticed something. 1 minus p over p. No, this thing I just noticed. It's sort of new to me. It is p1 minus p is the odds. This is a slight error. So if you guys are looking at it, fix it. Odds. I just noticed that I had put it upside down. The odds of something happening is probability of its happening over the probability of its not happening. So it slipped me. Okay, good that I noticed it. So that's that. So total surprise. Now, when you're doing flip coins, etc., then the average surprise that you have per trial is called the entropy. Now, and it comes out when you work it out. Negative p log p, which is the traditional form in which you see. Now, when you're talking about the loss function of a classifier, a good model would produce the evidence, the data. If you know that the ground truth is, it's a duck, it should say probability of duck is as close to 1 as possible. So the element of surprise would be again, the reciprocal of that. If it is not, for example, if the probability of a duck, it says 0.1, you should be hugely surprised. So that is that. And so if you add up all the surprises from each of the data points, how surprising the results are, or you can call it unpleasantly surprised you are at the results if you classify. The sum total of that is the loss function. And we can do the loss function, the probability, because probability you model as a continuous function, you model as some function. So the basic idea is for classifiers, so this needed to be said, so let me say, the probability is a function of the input. You expect it to be some function of the input, right? It's some probability function of the input. These are the same thing. Right? But because it's a function, you can take its derivatives, you can do gradient descent. So a loss function written in terms of probability is amiable to the whole machinery of optimization, of gradient descent, and any of the other optimization methods. Whereas if you take a number like the error rate or something, you can't do. It's a little bit harder to do gradient descent straight from that. Now, so cross entropy, we said, is basically the total, how surprised you are with the duck's results and how surprised you are with the cow's results. That is it. So we summarize all of that: surprise, entropy, cross entropy. Now, cross entropy has another derivation, which is in terms of the likelihood function. So likelihood is often misconstrued, and people think of it almost synonymously. They confuse it with probability. It's slightly different. Likelihood is the probability that a given hypothesis will produce the evidence that's actually there. So suppose you have evidence, data says rain, rain, dry, rain, rain. You may have two probabilities. You may be in, let's say, Phoenix, Arizona, or you may be in Seattle, Washington. First hypothesis, if you are in Arizona, then you would realize that the total cumulative probability, the joint probability of happening, based on your initial hypothesis that chances of rain is just 10%, will be much lower. The likelihood will be much lower, which is the joint probability. The likelihood that you are in Seattle would be much higher based on this model. And so the evidence has supported the hypothesis that you're likely in Seattle, more likely that you are in Seattle. The maximum likelihood estimation is essentially the very intuitive process of saying, given all the hypotheses, pick the hypothesis that produces the greatest likelihood of producing the evidence, or the data set. Data set is often called evidence in this way. Okay? So it is most likely to have produced this evidence. So that is a maximum likelihood hypothesis, or maximum likelihood estimate. When you use the maximum likelihood estimator, how would you maximize that in terms of your probabilities of cows and ducks? Let's say P's are the probability of ducks and Q's are the probability of cows. You just multiply that with joint probability, whatever evidence that you see, and then you maximize, find that value of P that maximizes. Well, maximizing product of probabilities is tricky because computers tend to deal with floating point numbers in a way that is suboptimal. We don't know, because we have finite storage, or we don't have infinite precision. So product of small numbers, fractional numbers, is fraught with danger. Fortunately, it turns out that if you have a product of numbers, you can take their log, because log is a monotonically increasing function. Finding the max of a function is pretty similar to finding the max of the log of the function. And so if you take the log of the function, then you can maximize the log. It becomes addition, because the log operator converts multiplication to addition, which is much better. Now you're less likely to have underflow problem during numerical computation. But then furthermore, it turns out that most optimization libraries or functions, they like to minimize things rather than maximize it. So that is easy. Just take the negative of the log. And so thus the end result, that the loss function is the negative of the log likelihood. Negative log likelihood. I should have written that sentence. Let me write it down. There's a famous phrase that people use: negative log this is an important milestone phrase for us in our journey. So you say loss for classifiers is given by negative log likelihood. Now comes the question, is this the only way you can capture the loss function for classifiers? It is by far the most popular way. But there are many adaptations and variants of it. Okay? And especially when you do deep neural networks, there are all sorts of losses called contrastive losses, many other forms of losses that come in. But this is by far the most popular, the most used, and the most intuitive to understand. So then now with all this architecture, let's go back and do some actual classifiers. We learned about two classifiers. I said that there is one classifier that people tend to ignore or not include in their analysis, and that is a mistake. As people who are learning from here, from support vectors, I would strongly encourage you, start your analysis with a dummy classifier. Why the dummy classifier? Because it sets the baseline. It is the same thing as the null hypothesis. Dummy classifier says, what is the performance if you ignore all of the input and you just look at the majority class in the output? Whatever, and that accounts for class imbalance in the data set. So for example, if you're screening 1,000 people for, let's just say, any common form of cancer, let's say you screen them for a breast cancer, which screening in the United States is very prevalent. When amongst women, of course. So when you do that, maybe in reality, the ground truth may be that out of 1,000, 3 or 2 or maybe 1, or one person has, or let's say 3 people have genuinely cancer on average, right? If you were to randomly take a sample of 1,000, on average, you'll find 3 people to have cancer, the breast cancer. So if you just, a dummy classifier would look at it and say, oh, 997 people don't have cancer. So one easy way, just say that whenever any data is given, just ignore the data and say, you don't have cancer. That is a quack doctor. Now, the doctor would be right 99.7% of the time. Astonishingly accurate. And so the doctor perhaps would get famous for the validity of his diagnosis or diagnosis. But of course, the doctor is a quack, because the 3 crucial cases that he should have got, he missed. And the difference between a quack and a real doctor is that a real doctor would catch those 3 cases, would do a diagnosis or use x-rays or whatever means necessary, and would come to the conclusion the radiologist would catch and say, yes, I see cancer. Okay? So a good classifier, therefore, it's like a good diagnostician. It should be able to pick that rare event. In other words, your classifier must do better than the dummy classifier. That is a measure of learning. If it doesn't do better than the dummy classifier, it is no good. It's, of course, embarrassing if it does worse than the dummy classifier. Right? So you should watch out for that. You should always compare your results to the dummy classifier. It's often called in literature the 0R classifier. The importance of this was, obviously there's a lot of literature that have emphasized this, but we'll come to that, to a few very good articles that talk about it. But then the more meaningful classifier, we talked about logistic classifier. Logistic classifier is often called the logistic regression, right? And you have to be aware that it's a misnomer. It is not regression, it's actually a classifier, and it often trips people. So under no circumstances think of it as a regression algorithm. It is a classifier algorithm. So in the interest of caution, always use the word logistic classifier. Just omit the word regression and you'll be better off. What does it do? We took the example of blueberries and grapes and their sizes. Take this example as a mental picture, and we will use it for many examples going forward. You have to determine whether a piece of fruit, so let's say this, well, my grapes are green, but imagine that I should have got red grapes. So a green grape, you don't know what this is. Is this a blueberry or is this a grape? And for a moment, imagine you can't see the color. So you would say that small, light things are blueberries, slightly heavier, more voluminous things are grapes. And so on the weight and size axis, this is the distribution of blueberries and grapes. Now, there may be some grapes that are very tiny, and there may be a few blueberries that are ginormous. And so in this feature space, this space you call the feature space, or the input space. In this case, why am I writing this blackboard R2? Anyone? Would somebody like to volunteer?
Real number?
It is two-dimensional. This means that it's a two-dimensional. So remember, this is two-dimensional real space, right? A real number space, right? You need not even say Euclidean. You may impose whatever metric you want, but Euclidean is a real valued space, though often implicitly it's Euclidean. So remember, guys, when you write this as a thing, n, it stands for n-dimensional space. And when you do that, the underlying assumption is that it's real valued continuous space, right? So your data, would you agree that if weight is one axis, this is x1, and this is x2, what is the dimensionality of your input space? It is 2. So it's a two-dimensional space, and that's the notation. So guys, see, remember that math is just an elegant and abbreviated way of writing something. There is no mystery to math. If math is not self-evident, then we haven't understood. But most of math is very simple. In fact, I would argue that of all the subjects I have studied in my life, I've always found math the easiest, simply because it is a set of very obvious things. One thing follows from the other with a little bit of thing. So you can have a journey of reasoning throughout the whole thing, unlike some other fields in which it is far harder to figure out what is going on. Economics, for example, is terribly difficult. It's hard to get two economists to ever agree sometimes. So those are hard subjects. Anyway, so we looked at this and we observed something crucial. First thing is we learned the concept of a decision boundary. So here we drew a straight decision boundary, which is what a logistic regressor tends to do. It takes a linear, that's why it's called a linear method. So logistic regression is a linear classifier. What does that mean? It draws a hyperplane decision boundary. Well, in 2 dimensions, a hyperplane is nothing but a line, but you can now generalize to 3-dimensional feature space, 4-dimensional feature space. It will be a hyperplane. What is the defining quality of a line or a plane and its generalization hyperplane, which is that the perpendicular vector points in the same direction everywhere, isn't it? That's the nature of it. So now, if you draw this big green thing that you just drew is, sorry, just let me take a photo. Yeah, so this thing is a very crucial thing. Geometrically, Classification is nothing but the search for a decision boundary, right? Or may I write that sentence? That if you look from a pure geometric perspective, which I find to be a more intuitive way of understanding machine learning, I will say this statement: a classification. To learn a classifier is to have discovered a decision boundary. This is an important statement. So it's a geometric way equivalent of this lot of algebra and so forth. It's as simple and as intuitive as that. Right? But all classification is a search for a decision boundary. In the case of logistic regression, it's a hyperplane. But you will encounter algorithms in which it won't be a hyperplane. It will be just any manifold, any surface, hypersurface that separates it out. And not just a hypersurface, a smooth continuous hypersurface is a manifold that we distinguish it out. Now, look at this. We talked about the intuition that the distance from the decision boundary is a pretty good predictor of whether it's a grape or not. If you're in negative distance, quite likely it's blueberry, very huge negative distances. Or for high positive distances, it's definitely grapes, isn't it? So for example, a huge negative distance is being here, this point A. You would agree that this point where my cursor is certainly a blueberry. You're pretty certain about it. On the other hand, a point like this, D, is certainly grape. With high degree of certainty, you can say. But as you go from A to D, you would realize that your certainty that it is a blueberry keeps decreasing, and your belief that it is a grape keeps on increasing, isn't it? Your belief that it's a blueberry decreases, and your belief that it's a grape increases. So if you take the grape as the positive case, here the probability of a grape at A is very low. As you keep moving forward, the probability that it is a grape keeps on increasing monotonically. And the important word is monotonically. There's no reason to believe that your belief decreases as you go around this. In fact, it continuously increases. So therefore, we are searching for something that creates a probability relationship between your belief is probability, that probability that it's a grape as a function of the distance. So how do we do that? So there we did a little bit of an intellectual gymnastics, very simple thing, right? And there are many, many ways you could do, but logistic regression is the most obvious way. You say that, okay, probability goes from 0 to 1, but distance goes from minus infinity to plus infinity. So how do I deal with that? Well, let's do one thing. First, convert probability into odds, because then it will go from 0 to infinity. You happen to know this trick. And as you know, common people talk in terms of odds, not in terms of probability. So P over the probability of it being a grape divided by probability of it being a blueberry is the odds. P over 1 minus P. Then odds are better. Odds go from 0 to infinity. See, probability goes from 0 to 1. Odds goes from 0 to infinity. So we are getting somewhere. And now if we take the log of odds, it goes from minus infinity to plus infinity, which, it so happens is exactly the domain of, is the range of values for distance. So the most intuitive theory that you can build out of it is to theorize that maybe log odds is the distance. The probability and the distance are the same thing. And that's the logistic regression, logistic classifier. And this is it. And this is how I remember it, distance function. And I also said that the distance function is given by an expression, which I didn't prove. It is this. But when you plug these two things together, you get the more traditional form of way in which this is a more traditional way the same thing is written in books. But the books don't tend to write the way I write. So I wish they did, because to my mind, it is simple geometry. It makes it look common sense, whereas this equation, the more traditional equation like this, is, I don't know about you, but to me, if I were to encounter this for the first time, I would be scratching my head and saying, where in the world did this come from? So anyway, that's that. So this, how does it look? The probability looks like this. It is a sigmoid function. When you are deep into the blueberry territory, the probability of it being a grape is 0. Then gradually, as you come closer to the decision boundary, it begins to be less and less 0. It begins to rise up. After crossing the decision boundary, it begins to cross 0.5 and move towards 1. And when you are sufficiently in the grape territory, you have driven into the grape territory, then the probability that it's a grape saturates around 1. So the word saturates, the mathematical word for that, and you should always use simple language. The mathematical word is the asymptotes. The 0 and 1 are the asymptotes of this regression function. Now, that's where we start. Now, this thing, the distance function is given by that. I'll keep it as an extra time, perhaps today afternoon or today, or in an extra session that I'll announce. Now, in this course, I wanted to make an announcement. I will be giving, so today, we'll finish classifiers. Today itself, I will take perhaps an extra half an hour also, because there is a bit of theory that I didn't cover. I'll finish that before going into labs. But then next week is, instead of doing clustering, which is the next topic, I want to do a topic called regularization, which we have not covered so far. So we will do regularization, and the week after that, we'll do clustering. So in other words, I'm extending the course by 1 week, simply because we have missed, at the pace at which we are going, we have missed a crucial topic. So please note it down if you have any travel plans and so forth, that this course is extended by a week. We will do regularization next time and clustering the week after. So next week is regularization. So before I go into the lab, let me talk about another classifier which is worth learning about. And so there are many, many classifiers, but we are sticking to the simple ones, the linear ones. So there is another classifier which actually predates the logistic regression by many years. Logistic regression, despite the simplicity of the idea, is surprisingly recent. It was discovered surprisingly recent. I believe in the 70s or 80s it was discovered. But there's a classifier that was discovered even before that, I think in the 20s, and goes to that data scientist or statistician, Fisher, who we talked about, let's say, in polite terms. So this is called linear discriminant analysis, LDA, and something called quadratic discriminant analysis, QDA. These are the two. And broadly, they are called discriminant analysis. If you don't want to discriminate between the terms, just call it analysis. It's based on a very simple idea. And let me illustrate the idea with a single dimension. So suppose you're looking at, let's bring back our ducks and cows. Okay. Cows and ducks. Let's look at one attribute. Pick an attribute. Let's say weight. So if you look at the weight of our animals, would you agree that most of these ducks, they would be having weights? If you make a histogram, the ducks would be sitting here close to 0, very, very small values, whereas the cows, what color should we give the cows? Let's give cow a nice, okay, I'll just give it this color. Cows have a much greater variance of weights. So let's say that cows if you plot out the weights, well, obviously this hardly looks like a histogram, but imagine that it is a histogram. Right? So would you agree that if this is the x-axis, the one feature, which is the weight, most of the weights of the ducks would be piled here, ducks. And this would be the region for the weight of the cows, because cows weigh what? I don't know, maybe 600, 500 pounds. Anybody knows what's the average weight of a cow? Would just somebody please look it up? Albert, can you please help me? What's the average weight of the cow? Ducks, let's say 10 pounds. So what will happen is the duck will have a mu of the duck is equal to approximately, I don't know, what's the average weight of a duck? I'll just hazard a guess, 10 pounds. And if you look at 1600 pounds, oh,
that would mass. Bull is 2400.
Oh, so cow is 1600 pounds. Are we together? Are we together, guys? So what happens is these two, they have vastly different weights. The mean of their weights are here. Also, the duck's weight varies in a pretty small band. Like, I don't know, a newborn duck maybe what, 3 pounds, 4 pounds, and maybe 2 pounds, tiny little duck, and may grow up to, let's say, 20 pounds. I don't know if a duck is ever 20 pounds, but let's make a guess. So it has a pretty small band, variances. It sort of ranges this to this, maybe, let's say 5 pounds to 15 pounds, right? 5 to 15. Whereas in the case of a cow, it may be easily, this may be, let's say variance of the weight is somewhere from, I will just hazard a guess, 1,000 to 2,000. Just the core weight, yeah. Does this look reasonable, guys? It would help actually if some of you gave me some feedback, so I knew that I'm making sense to it. Are we together, guys? Anyone?
Yeah.
So if you now want to make a classifier, you can see that, and you can say, well, it is just dead simple. All you need to do is draw a decision boundary. Take these lines. Take this line here. Let me just call this the mu1, this line, and find its perpendicular bisector. This line, find the perpendicular bisector, which would be probably here, right? This point, because it's a one-dimensional data, only the weight, this point, which is the midpoint between the two mu's, is a good separator between the two, isn't it? So mu, the decision boundary mu, right? Or you can just say that the decision boundary is at mu of the duck, the center of the duck hill, right? Plus the center of the cow heap divided by 2. Would you agree? Right. I hope this is simple intuition. Just go and pick the midpoint between the two hills.
Oh, shouldn't it be like the mu of cow minus mu of ducks by 2? Or it's the same?
It will be the same.
Okay.
The average. So it will end up hitting there. Right? So
No, as if I think Raj was correct. Mu cow minus mu duck by 2, I think, perpendicular bisector.
that is true. So think about it this way. This is, so this part is mu duck, right? And now this, if you do this point, like this distance, if you go half the distance here, you are saying that it is mu cow minus mu duck divided by 2. But then to get to this location from the origin, you still have to add the mu duck. So add mu duck to this, and it will become, what will it become? Mu cow minus mu duck plus 2 mu duck over 2, which is the same as this. Are we getting it? Because you have to
Yes,
always
if we got it. Sorry, we thought it's from mu duck we calculated. We never thought it's from 0.
So this, it turns out, now let's generalize it to higher dimensions. We remember that we didn't just take the weight of the cow and the duck, we also looked at its size. So let's go to 2 dimensions now. Our little feathery creatures, their mu size is the centered here. As you know, both their weight and their volume will show a normal distribution, a bell curve distribution. So you will end up with a, should I use an intuitive term, a bell hill? A generalization of a bell curve. This is a bell curve. And this also, both are bell curves, right? If you do a histogram of the weights, the histogram will roughly look like a bell curve, doesn't it? So what do you call a 2-dimensional bell curve? A bell hill, let's call it. The technical term is not bell hill. Technical term is, it's still a normal multidimensional normal. It is still a normal distribution. That's a technical or Gaussian distribution. Except that it is 2D, 2-dimensional Gaussian distribution. And well, this is the weight axis. This is the size axis. Well, as you can see, ducks are small and light, but cows are big and they will be centered around here. And so they will be clustered. Does this make sense, guys? So that if you were to project the data on the weight axis, it would be roughly speaking a bell curve here. It would be here. It would be also a bell curve. I'm just inverting the bell curve so that I don't go about overlapping things. This would look like a wide bell curve here. This is weight. Would you agree? And the same here. Here, a bell curve, blue. If you project it on the, if you take the shadow of this data on the, it's called projection. Project it on this, you would expect the bell curve of the cow to be here, isn't it? So common sense says that, hey, for 1 dimension, we took this point as the decision boundary. The same thing we can apply to the second point. What do? We take this. So when you take this, now we know 1 point in the decision boundary, but that is not enough. We need to, in 2 dimension, we need a plane, we need a line. So where should the line go? Let us use the same common. Should I make the line tilt, let's say, like this? Is this a good tilt for the line as a decision boundary? Or should I pick a line that is like this? So should I pick
the second one was better?
And why is the second one better?
Because the second one exactly bisects to the plane. To be true, the first one is like it's nearer to both of them.
That's right. So what you say is, you know, if you take a different sample of data, you're much more likely to make mistakes with A. Right? It's too close to the data. You want a plane, a decision boundary that separates the data away from itself as much as possible. And because that will be a more stable solution. You know that if you take different samples of the data, you are not going to, your decision boundary won't change if it happens to be B rather than A, isn't it? And so you say that your decision boundary is the perpendicular bisector of the line connecting of what? Of the line connecting the two, isn't it? Well, this is, imagine that this is, this becomes your decision boundary. Very simple intuition, as you can see, not any complicated mathematics here. It's the decision boundary here. Just take, now, what are we saying in this way of looking at it? What exactly are we saying? Let's look through this. We are saying that it is, if this is a decision boundary, and once again, this point, mu of the decision boundaries point, this point, let me just call this point P. P is at, now you know that mu, now comes an interesting complication. This mu, let's look at the bell curve. This point has a x1 axis and a x2 value, right? It has a value along the weight, the average weight of a duck and the average size of a duck. So you can say that for the duck, mu of the duck is now a vector. It is mu1, mu2. Would you agree? For the duck, mu1 duck, mu2 duck. Let me just say duck. Likewise, you would agree that this is a point. It has a xy coordinates, right? Or x1, x2 coordinates. So mu of a cow is also a vector. That is mu1 of a cow, mu2 of a cow vector, isn't it? And so you're saying that the point P, again, is exactly the same reasoning applied. It is mu1 duck plus mu1 cow divided by a half of, and this is mu2 cow plus mu2 duck. Doesn't matter. I'll write it just for consistency. Would you agree that it's the average of the two vectors? Right? The point. And the direction of that is obviously the perpendicular bisector. So when you use this approach, you are doing linear discriminant analysis. And that is the so there are some underlying assumptions to this. One of the assumptions that you have is so assumptions. The assumptions are that in the feature space, the points, the data points for each class, data for each class. What are the two classes here? Cow or duck. Show a normal distribution. This is an important assumption. Would you agree, guys? This is one underlying assumption we made. For example, this assumption doesn't quite hold for our grapes and blueberries. Do you realize that? If you look at this example of grapes and blueberries, do you feel that all the blueberries are nicely forming a bell hill? In this particular case, they don't seem to be in this particular case, or this particular sample of data. So that is why it's an artificial example, because in reality they would. The grapes also, they're separated out, but I wanted to illustrate a point. Now what has happened? I seem to have lost this. Where am I? I think I have to wait for this thing to catch up. So this is one assumption. The second assumption is the hills have each the same variance. What does it mean? This is let's say that this is for the duck and this is for the cow. You just make, you know that the variance of the cow is much more, of weights of the cow is much more than that of the duck. But as a simplifying assumption, you say that the sigma square of duck is approximately sigma square of the cow. Means both the classes have the same weights. So remember that assumption may not be true. In fact, is not true in our case of cows and ducks. But linear discriminant analysis, it just simplifies the problem. It says that assume that they are the same. And then just find the perpendicular bisector of their centers, the central variance. And that is your decision boundary. When you make these two assumptions, you're using the linear discriminant analysis. So it tends to it draws a linear hyperplane through the data. Okay, so this is an important thing to draws. The second thing, and we are almost done, if you violate the quadratic disk analysis, basically says here each hill can have its own separate variance. That is, sigma duck is not equal to the variance of the cow. Right? So if you make this assumption, now you're in a bit of a trouble, because see, in linear discriminant analysis, you need to find just mu1, mu of the duck, mu of the cow vector, and a common sigma square. But here, so there are three variables that you need to evaluate. In quadratic discriminant analysis, you have four variables. There's the mu cow, mu duck, there is a sigma cow, sigma squared duck. So there are four variables. And what does it do in the feature space? What it does is this makes, and you can take this as a fact, but we won't have time to prove this. This makes the decision boundary a quadratic curve. So what are some quadratic curves? A quadratic curve or hypercircles. So in 2D, can you mention what are some of the quadratic curves?
Like a parabola?
Yes, parabola.
Ellipse, circle, hyperbola.
Yes, etc. So it will be any one of these. Huh? These are two-dimensional surfaces. So your decision boundary won't be straight. So this is something to know. And as you can see, the derivation of reasoning through a linear discriminant analysis is a pretty straightforward, and we quickly went through. So in this course, we will stop because we are only doing mostly linear methods. We do that. Now, classifier is a rich literature. It turns out that classifiers are by far the most commonly used machine learning algorithm. Real world, all sorts of situations spec for a classifier as a predictive problem. So how many classifiers are there? Algorithms are there? Practically countless. If you, lots and lots of new classifiers keep showing up on the in the community all the time. If you're in a hurry to publish a paper, go create your own classifier. You want a quick PhD, go write, come up with a very interesting classifier that meets the state of the art. Lots of classifiers. The same is true for regressors. There are many, many regression methods, though I would say that in the classification literature is a little bit richer. Are we together? Yes. And the range of classifiers and regressors or predictive. So these are all called supervised learning. See, whenever you make a box in which you put some input and you're predicting a value, it's called supervised learning because you need to train, you need to make the machine learn from training data. Whenever you're training the machine on data, and then once it is trained using it for prediction, it's an example of supervised learning. I don't like this term supervised, unsupervised learning. So I tend to just say Like prediction boxes are regressors and classifiers, right? Prediction machines are regressors and classifiers. Now, that is that for today. Now let's take a 5-minute break. We have been talking now for an hour. If there are any questions, please ask me. Otherwise, we'll take a 5-minute break. And after that, we'll launch straight into the labs. I'm pausing the recording. So we did linear discriminant analysis, quadratic discriminant analysis, and logistic regression. We will use this in our labs. Now, I must say one thing, that the LDA here, LDA in machine learning has actually, unfortunately, two different expansions. One is linear discriminant analysis, and the other is a topic that we will learn one day when we do natural language processing in your ML500, which is called latent often used for e.g. topic modeling. You use it for topic modeling. So be careful which of the two, this acronym in different domains have different expansions. Right? So just be on the guard for that. All right, so with that being there, now onwards to the labs. So first, okay, precision and recall. Let me just explain this. The best way to do that is, look at this picture. Let us say that the green side, the left-hand side, are all the dots that are truly positive, right? So green zone is positive zone. The gray zone is the negative zone. All of this data on the left-hand side of this square are all genuinely positive, right? And all points on the right-hand side are genuinely negative. And let us say that your algorithm, what it did is, it managed to call this subset of points inside the circle, the dark green points, as positives, right? And it managed to call these points here, right, also as positives. So now what has happened? If you think about your algorithm, which parts are mistakes? Which of these two parts? If it calls everything inside, if your algorithm calls everything inside the circle as positive, so it made two kinds of mistakes. First, it identified a lot of points out here where my mouse is in the pink area. They were actually negative, but they are marked as positive. They're predicted as positive. That's a mistake, isn't it? So those are false positives. But at the same time, these points were negative. These points were truly positive, you know, because the whole left-hand side is made up of positive points. But your classifier missed all of these points. Because it missed all of those points, it marked them as negative. And so it ended up with a lot of false negative. These points are actually positive, but it marked it as false negative. So in a very geometric way, see, there are formulas for precision and recall, but I always like to, one advice that I would give is, this is perhaps the most intuitive picture I have seen of precision and recall definition. Precision is how many true positives you found out of everything that you called positive. So in other words, if your precision is high, you will have a low false positive rate, right? So it's precise. It manages to pick up the right, when it calls something positive, it quite likely is positive, right? Recall, on the other hand, is picking the proportion of the positives that it found compared to all the positives. how many positives did it find? So suppose there were in a population of 1,000, let us say that 10 people had cancer, and your classifier found 3, predicted 3 as having cancer. So it missed the other 7. So what would be the recall be?
3 by 10.3.
3 by 10, right? Because 3 out of 10 it got. On the other hand, it marked, let's say that it got 3 of those positives, right? But it also marked 4 of the negatives as positives, isn't it? So what would the precision be?
3 by 7.
3 by 7, exactly. So it marked a lot of, it also had a lot of false negatives. So now let's make it all real, guys. See what happens is in medical, no test. Medical is a science which is quite soft in the sense that human body is profoundly complex. There's a reason, I believe at one point it used to be called the terra incognita, the unknown territory. Much about the human body is still not known, correct? Despite all the progress of science and medicine and miraculous, amazing progress, still most scientists believe that we are barely scratching the surface. There is a lot about the human body, about all the biological processes that we don't understand at all. Okay? Basic things we don't understand about it. So here, even questions like, do you have a particular disease or not? One test doesn't work. So the way you do that is you generally have screening tests. In the US at least, you have the first course of action is that they will do a screening test. Let's say it's cancer. You would do a screening test for cancer. Then if you turn out positive, then you just become a suspect. There's a suspicion of cancer. Then you're sent to another test which confirms whether you have cancer. So tell me, in the screening test, which would you aim for? High precision or high recall? If you had to pick one and get that right, which is more important, precision or recall or accuracy? Articulate some guesses, guys.
Precision.
Precision, because you want to, the ones that you mark as having cancer should have cancer. But precision doesn't account for the fact that you missed a lot of people who did not have cancer. Who had cancer, but you missed them. The false negatives. Remember, precision will not be affected by a lot of false negatives. It is only affected by false positives. But what will happen if you have false negative is that would be catastrophic, isn't it? Because you send a lot of people happily home saying you don't have cancer. And by the time they come for the next checkup in 6 months, you have progressed to a pretty advanced stage of cancer, doesn't it? So for a screening test, precision does not seem to be as good a measure to shoot for. Or what would you shoot for? Accuracy also is not terribly useful when the data is so asymmetric, because a very rare number of people have cancer. It turns out recall is, because what recall looks at is the proportion of true positive amongst the positives. Like of all the positives, how many did you find as positive? Even at the expense of false positives. A good screening test will capture all the positives as much as possible. But it may make mistakes. It may also mark a lot of healthy people as positive cases for cancer, isn't it? So in a screening test, you would rather have high recall. Guys, are we understanding it? In a simple screening test, you want a test that has high recall. It shouldn't miss the positive cases, right? So recall is what? Proportion of what you found over the total number of cases. So when the recall is close to 1, what does it mean? It means that you caught most of the cases. Are we together, guys? In screening tests, you want that. Now, but after that, when you're going for a confirmation, you know that by now, a lot of the negatives have already been weeded out. But in the final test, which is right before surgery or aggressive treatments like chemotherapy and radiation, what do you want to do? You want to have, you want to weed out what? The false positives. So you want to make sure that the ones that you mark as positive, right, are truly positive. You don't have false positives. You don't want to put a healthy person through massive doses of radiation and chemotherapy. Okay? So as a final diagnostic test, before aggressive treatments are enforced, you want high precision. Guys, am I making sense?
Yes, Asif.
Yes.
That is it. So that is the intuitive difference. One is not superior to the other. It is based on the use cases. And do you notice that in between both of these use cases, the one measure that wasn't terribly useful was accuracy or error rate, or its converse, the error rate. So it is rather unfortunate that many textbooks in this and articles and blogs and all these Kaggle notebooks, when they do classifiers, they tend to be a little too fixated on accuracy. What is the accuracy you're getting? That generally, and it becomes a habit. It becomes like the p-value that statisticians develop for quite a few years. You shouldn't think like that. You should think about the problem and ask, for this situation, what is a good measure? What should I shoot for as a diagnostic measure? You have many. For example, you have precision, recall, you have accuracy, you have error rate, you converse the error rate, and you have area under ROC curve, right? So you have to consider all of these things together, right? And pick the best one. For screening test, pick high recall. Or for the final test before doing aggressive treatment, do a highly precise test. That's that. And ask yourself in the beginning of an analysis, which one you should do. So, all right, with that, any questions? I'll end the theory now. I'm going to move into labs.
Asif, how about doing the test twice or thrice to confirm it? Do you think that it will lead any result, or it's just a stupid thing? It's like idiosyncrasy, expecting different result each time.
See, there is instrumentation error. Unfortunately, in medical, because these are biochemical reactions, and they work only under fairly strict laboratory conditions. The fact of life is every laboratory has a certain error margin, and that error margin is usually pretty bad, actually. For example, in India, the COVID tests are very unreliable. They get it wrong quite often, 30% of the time, right? So they mark a lot of people who don't have COVID as having COVID. They mark a lot of, and they miss a lot of COVID cases. Even in the US, the numbers were better, but even with a very sensitive RT-PCR, there was still a sizable error rate, right? And the recall was not good enough. See, a good RT-PCR test would have caught all the positive cases at the expense of some false positives. But from what I understand, it isn't perfect. Right? It's good, but not perfect. Fortunately, it is pretty good. The recall is quite high. So if it says you have COVID, you probably have COVID, right? Or you don't have COVID. Like most likely it got it. But it may also be true that you don't have COVID. It's a false positive. So false positive rates are there. But these are chemical tests. They're based on many factors. So remember that you do the same test in two different laboratories, you often get two different values. right? Based on how skilled the technician is. And so in US at least, every laboratories by government is required to give their error bar. Yeah. There's a quality metric and they have to declare what is the error bar. So for many blood tests, it is standard to send the patient for tests multiple times, at least 3 or 4 times to confirm. See, if you have only one test that you can do for that disease, then common sense says do the test at different periods of time, at least 3 or 4 times before you come to an answer. But fortunately, for many things like cancer, there are multiple modalities of testing. There are many different things you can do, some more precise than the other. So for example, in cancer, what happens is you do, the most aggressive thing you can do is core biopsy. You can literally go and take a piece of that organ or tissue, take it out, put it under the microscope and see whether you have it. But it's pretty invasive. Getting a core biopsy done of the liver or any other organ should not be your first course of action, right? Or doing a core biopsy of breast would be pretty traumatic. So you do it as a final test before you go in for radiation or something like that. You instead do a screening test, but you hope that the screening test has a high recall, even at the risk of producing quite a few false positives. So that's how it goes. And sometimes things happen, like for example, if you have a chest congestion, right? Or you just happen to have a little bit of a, something. You go for an X-ray and it may look as though you have lung cancer or some problem in the lung. 2 weeks later, you get the same screening done. It might all be clear. So human body is complex. There are no definitive answers. Any other questions, guys? So I'll start the lab with something that I wanted to show you. We talked a lot about correlation, and what correlation means and so forth. So you will find that I have created where is that gone? Let me start it again. Okay. Localhost 8501. Okay, guys, I'll show you a little demonstration. Right? This code also I put on the course webpage. Oh, by the way, I must mention that I've released a lot of notebooks now. The total number of notebooks there on the website now is 25, which means I highly encourage you, if you want to get the most out of this course, to go and study all of this code, understand all of them. I have released, so lots and lots of them. Some of them I've not covered. For example, Florence Nightingale is just for you to have fun, to see how beautiful visualizations can be created, landmark visualizations can be created. But I've released a lot of things that it is worth studying carefully. There are 25 notebooks, and by the time the course is done, the number is likely to get to 30. Actually, not 30. I've released about 30 notebooks. So it will go to 40 notebooks. Right? So please keep studying the notebooks. I can cover only some of them in the class. I can't cover all of them in the class. So we'll take this data. Once again, what do we do with the data? We load the data. So guys, this notebook is already on the course portal, and you can. I would ideally like you to go and follow this, do it on your own, because my walking you through, today I'm walking you through in the interest of time, because we have a lot of territory to cover. So I can't wait for all of you to do it. But I trust that you are doing the homeworks. If you're not doing the homeworks, then it's counterproductive, guys. Practice makes a man perfect. So unless you practice, unless you do things on your own, it is no use. See, there's no point in watching world champions play tennis. You won't become good at tennis. You have to go to the field and play tennis on your own. You see the point? And most mathematical disciplines are about practice. Once you understand, first you learn, you listen, you understand, you learn, and then you practice. Make it a part of your life. And then it's coding. So making that. So I take this data, by the way, I added a little bit of style just to show that you can add styles to things. Just to make it look prettier. So here are values. It contains 3 fields, x1, x2, and t. T is the target variable. T you have to predict. Right? Now, t in this particular case is either 0 or 1, but it's not obvious from here. If you look at a few lines of data, you will see. So what I am doing, after you look at the data, this data, by the way, we can open in, let's open it in a tab. And when you open it and see a few rows, you can see that it is. Do you see what are the 3 columns of the data? X1, X2, and T. Like X1 here is 6.227. X2 is 5.372. But if you look at T, its value is either 0 or 1. Right? Always 0 or 1. So it is the target variable. It's supposed to be, you can think of it as cow or duck. Are we together? That's your target variable. So let us visualize this data. And one of the things you should do is, of course, convert T into a categorical variable. It's a class. But I've skipped this. I'll let you do it. When you visualize this data, you again make a scatter plot, just as we made, except that now you can specify the color of this. You see, the color of each of the dots should be based on the value T value of that record. Right? The third column, T value. So this is it. The rest of it, I hope you know, S is for size. So what happens is if you just make a vanilla scatter plot without prettifying it, it doesn't look so beautiful. One of the things that I've been emphasizing is, if you want to create publication quality work, you should always spend some time on the aesthetics of your graphs, of your visualizations. It matters a lot. Right? So here we go. S is for size. Alpha is for, what in the world is alpha for? Does somebody remember?
Opacity.
Opacity. So this is not size actually. Let me move it here. This was size. This is opacity. Or opacity, transparency, whatever you want to call it. And C is the new thing we introduced. It is data. Which column of the data should you base the color on? So you're saying pick the color based on the value of C. And now I'll introduce you in visualization to the concept of color maps. So when you visualize colors, one of the things in data visualization that happens is you have to be sensitive to the fact that 30% of men are colorblind to different degrees. And so I don't know if it is prevalent amongst women. I'm told it's relatively rare, but 30% of men are colorblind. Right? So you need to pick colors that they can separate out. They can't see certain colors. It doesn't mean that they don't see any color at all. They just can't see certain colors properly. Right? So you have to pick colors when you are separating things out, sensitive to them. So Matplotlib and all libraries, they recommend that don't randomly pick your own colors. Instead, pick colors from very safe, known color palettes. Right? Those are called color maps. And Matplotlib has a pretty rich set of color maps. You can pick any one of them. Red, blue, RD is for red, BU is for blue. Obviously, you can see red and blue here. So let's go and find all the color maps available. So here we go. Color maps tutorial. classes. There are lots of color maps here. So you can have a sequential color map. By the way, Viridis is pretty popular. Quite often you see it being used. Now, you can have a monotonic color map like yellow, gradually going to red, or red-blue. Where is my red-blue? Red, purple. So, no, it's not here. See, it must be, where is my red? The one that I'm just using. And you can have three colors, yellow, orange, brown, and so forth. Red, purple, blue, green, purple. Let's see, maybe sequential map 2 will have that. No, it doesn't have that. Okay, divergent colors will have that. So you can see that there are different color maps you can choose. Right? Red, blue, yeah, it's very divergent. If you use a divergent color map, then the things will really stand out away from each other. You can have cyclic color maps, and then you can have discrete color maps. If you know that you're going to have only a few classes, you can pick things from discrete. By the way, this tab 1, tab 2, tab 3, tab things, these are the ones that the software Tableau tends to use, I think. So, and then there are miscellaneous color maps. You can use whichever one you like. So there are many, many color maps, and each of them has been carefully thought through, validated. And when you create your visualizations, use a known color map. Okay? You can play around. I'll let you discover the beauty of all these color maps and find which one strikes you as beautiful and what you would like to use. Okay? These are examples. Use that. So we learned something about today. We learned color maps. The rest of it is simple. The x-axis, the y-axis. Yes, as I said, I use LaTeX. I don't know, did you all install LaTeX? How many of you installed LaTeX? Anyone who installed LaTeX on their machines?
I installed LaTeX.
Very good, very good. It does make your documents look better, isn't it? So the next thing we will do is we will again use the red-blue palette, but we will draw just the scatter plot. And these are called these are smoothed out histograms. These are called KD plots. Right? These smoothed out histograms are called KD plots. Now, KD is a topic that merits its own little discussion. I will do KD. These are called kernel density estimates. It's a lovely, lovely thing. Its intuition is very clear. If your histogram was smoothed out, what would it look like? If you think that histograms are trying to tell you about a shape, what shape is it? That is called the density, KD. Right? So, by the way, this is a way to create a multiple plots code to do. Very simple. You say in the diagonal here, draw the KD plot. Right? So you see the diagonal as KD plot. Along the upper, above the diagonal, put the scatter plot. Below the diagonal, put the two-dimensional KD plot. Right? So what happens is it will make contour lines. The contour lines of where each of the types is more dense. So once again, guys, I won't get time to do visualization. You have to pick up visualization. If you find the code hard, please sit with us sit with the teaching assistants. They'll be very happy to help you or explain you. And if you look at the documentation of it, it becomes self-evident. Okay? So that's the visualization code. Now we break the code into the train and test. Right? First, we separate the predictors from the target variable. We always do that, remember? And then we separate the data into training and tests. We need to hide the test set under the hood so that the algorithm doesn't know about it while learning. Then we take a logistic regression classifier. By the way, Newton conjugate gradient is a solving method. You don't need to take it. Even if you just say logistic regression is good enough, it will by default take something. What do we do with our algorithm? From regression, we are familiar with it. All we have to do is take the algorithm and call .fit on it, or fit with the training data. When you do that, it will, and then you can use it to do predictions, and it will give you the predictions. Once it gives you the predictions, you can compare the actual value with the predicted value, isn't it? How do we get the confusion matrix? By looking at the actual value and the predicted value and seeing where they agree and where they don't. So when we look at this, by the way, did I do it in a more visual way? No, okay, we'll come to that. When you look at this, what does 295 suggest? This diagonal, most of them are true, like true positives and true negatives. But there are, how many mistakes are there? 25 and 26 added together, 51 mistakes, isn't it? So what we have here is precision and recall for each of the classes. The precision and recall in this case are pretty high. Now I'll introduce you to a new concept called F1 score. F1 score is a balance, like when you have a situation in which you don't particularly want to root for or emphasize precision or recall separately. You may say, this is a case in which I care about recall, or this is a case where I care about precision. But in general, if you don't care, like in this case, blue dots versus red dots, right? You don't really want to emphasize one versus the other. So then a very good metric to shoot for or improve is the F1 score. Right? F1 score is the harmonic mean between precision and recall. Do you remember what harmonic mean is from school algebra? I'll just mention it for a moment. Harmonic mean is, so let's talk about the various means. Mean, right? Arithmetic mean of two numbers is x plus y over 2. This is the definition. Would you agree? Right. Geometric mean is defined as x times y square root, right? Which is the same as xy to the power half. Harmonic mean tends to be 1 over harmonic mean is equal to 1 over x plus 1 over y. Right? And I believe there's a factor of half. Am I missing a factor of half here? One of you, if you could quickly. I don't think there is. Okay, maybe there is a factor of half. Right? So it is the harmonic. I don't think there. Actually, somebody.
I think it's into 2, I think.
No, there is a half factor.
Half.
So this will become, what does this become? This becomes like h is equal to, so if you solve this equation, this becomes h is equal to 2 times xy, x plus y. Right? But I tend not to remember it this way. I tend to remember as half of the reciprocals, average of the reciprocals. Right? This is harmonic mean. So when you take the harmonic mean, so F1 score is the harmonic mean of precision and recall. This is it. Are we together? This is its definition. So when you don't particularly want to emphasize one or the other, take the shoot to improve, train your algorithm to optimize on the harmonic. So here the F1 score is for both zeros and one is pretty good, 92, 94, close to them. Weighted average is 93, doing pretty well. Precision recalls are all 93. It means that this classifier is doing pretty good. Now, what does this classifier do? It's a logistic regression. So what will it find in the data? In this data, what will it find, guys? It will find
The divider, right?
0 or 1.
right? It will try to find a line like this, isn't it? Would you agree?
Yes.
Now, okay, now the trouble is I annotated it and I don't know how to undo the annotation. Oh, goodness, I have to learn that. This comes from Zoom, so please give me, oh, Claire. Well, Claire didn't help. Okay, undo it. All right, so let's go and find the decision boundary in the data. Your logistic classifier has found a line. That line will have a slope and coefficient. Would you agree that it will have a slope and an intercept?
Yeah.
Right. And yeah, so its values are given as, so the coefficient of this are this. And if you work out the slope, classifier coefficient, classifier intercept. Why? What is the equation that it has written? Right? The equation that it has written is see, ultimately log P1 minus P is equal to beta naught plus beta 1 x1 plus beta 2 x2. This is what it has written. Do you see this, guys? Okay. So I have this value, I have this. These are the coefficients, and this is the intercept. Right? Now, you see that. Then one of the things I said is that actually classifiers come up with a predicted probability that any point in the feature space, what is the probability that it is? Is the intuition clear, guys? If you create an algorithm here, what it is doing is, this may be your decision boundary. Okay? This may be your decision boundary, but it is also true that if you take any arbitrary point x, you will have a probability of x of being great. So any data value here with that size and that weight, you have a certain degree of belief that it is a grape or not. Here you would probably have less than half the belief. You would believe 0.3 is your belief, isn't it? So for each point, I'll write this statement. For each point in the feature space R2, right? For each point, let's say x in the feature space, there is a probability. There is a probability x of it. Guys, is this by now, after all the discussion, am I saying something pretty obvious? So every point, there's a certain probability. Now, if you want to find the probability, and the good thing is that the scikit-learn logistic regression actually comes out with those probabilities. So, you don't need both the probabilities. If you ask the classifier to give you the probability at a point, it will tell you the probability that it is a grape and the probability that it is a blueberry. You don't need both. Why? Because the two add up to 1. Exactly. So you just need one. You can pick the 0th column or the first column, doesn't matter. So you take that, you get the predictions. Now what can we do? You can use this to visualize the predictions. What we'll do is, we'll do some visualizations, all of these values being there. First of all, there is a library, Yellowbrick, very convenient. It can do all of your, remember we learned about confusion matrix, classifier report, and area under ROC curve. Now, there is one more thing that we'll talk about, feature importance. How much in making the prediction, how important is the X1 feature and how important is the X2 feature? And the reason that matters is, sometimes, for example, if you have diabetes and predict somebody has diabetes, how much does how much being overweight matters versus how much does some other factor. Let's say eating, certain how much salad you eat every day matter. So the two are both will affect whether or not you have diabetes, but one will have more impact than the other. So that is it. So that is feature importance. How important is this feature? So when you look at this, this is a plot I like actually. I like to do this visualization because in one single shot, it draws everything to you. This is the classification report. Then, by the way, it also puts T there, but ignore that here. Then, oh no, it takes the average of the two, not T there. Where am I? Did I? Yeah. So it gives you the 1 and 0, and it gives you the precision recall, right, and their averages. Now, it also gives you the confusion matrix. Here is the confusion matrix. How many cases did we get wrong? 25 and 26. Do you remember? But it puts it as beautiful colors. It says that in making the prediction, the second variable is a little bit more important than the first one. Maybe let's go look at the data. There is more variation along the second variable than the first variable. This one rather than this one. Because along the x1 axis, they are much more overlap than along the x2 axis. They are more separated out, so easier to make to use x2. If you look at the area under ROC curve, where is the area under ROC curve? I don't know, is it visible, guys?
Yes.
You see the ROC curve? Would you call this a good curve or a bad curve?
It's a good curve.
It's a good curve because it has a pretty high area under ROC. In fact, the area under ROC is 99%. It is hard to beat that. So you have a pretty good classifier. Remember, ROC curves, the axes are false positive, true positive. It achieves true positive rate pretty quickly. So now, getting back to zooming out again, let's visualize the model predictions. So one of the things we do that I do actually, and I would highly encourage you to do, is take this and at each point color it by the probability that it is a blueberry or a grape. And the way you do that is you say that if it is a blueberry, then mark it like this, blue. If it is a grape, then mark it yellow. Right? And so this is what we have done. In this particular case, it is the probability that it is a blueberry is high. So blue, otherwise, if the probability of a grape is high, then mark it red. So you look at the feature space. Do you notice that as you come closer to the decision boundary, which is the white line, the blue color becomes lighter. What does it signify? Anyone?
That's most probably could be a grape.
Yeah, you're getting your belief, your confidence that it is a blueberry is decreasing, right? And then somewhere in there are white dots. It means you're literally sitting on the fence. You don't know whether it's a blueberry or it's a grape. And then as you cross over the decision boundary, gradually you begin to feel more and more that you are in grape territory.
So, Asif, how did you figure out one you denoted as right?
Oh, right. See, because I taught it to you with blue and red, I made sure that the visualization deliberately agreed with that. So what I did is, if you notice, I picked the column for blueberry. This is one of them here. This column, if I had made it 0, the picture would reverse itself. Right? So it is like, you know, this thing, red, blue. Right? So then I would have had to invert it by saying _R, and it would exchange the color of blue and red. So these are just visualization tricks. So guys, this code, I hope it looks simple to you. But here the important thing is color comes from a continuous variable. It comes from the value of the prediction. Where did we predict? We use this as prediction. So guys, I wish usually before the pandemic era, everybody used to be here in class in front of me. We used to have a very interactive discussion and I could look into people's eyes and see whether you're understanding it or not. But we are in a new world of Zoom. So it is a little hard for me to get a sense whether you guys are finding it easy or hard. Do I need to repeat myself? Are we finding it easy?
Yeah, Asif, I think I missed something important. So we started this thing with 3 columns, right? X, Y, and T. T is the either T is the
Target.
binary one, right?
Target is a binary. Target.
So at what point or how did you figure out that the prediction is right or wrong? Where is that data coming in from?
See here. So what happens is I took the data, I visualized it. So clearly I see that logistic regression will work because you can imagine a linear decision boundary through this, right? So what happens is you do all the histograms. This is just data visualization. Then first thing, you split the data into test, train, etc. This is all. Then what you do is you build the classifier and you make predictions, right? Then comes the model diagnostic. Here is when you know that you have a good model. Why? What are the model diagnostic things that we learned in theory? The confusion metric, the accuracy, the precision, the recall, and the.
I think here is my problem. How did you know that a particular datum is right or wrong? Whether you predicted it as a grape and it turned out as a blueberry.
Oh, you can do that. You can emit out how many the exact data points where it made mistakes. You can produce a list like where Y is just another line of code. See, you know the actual value Y test, the ground truth, and you know the Y predicted.
No, so where did you get the ground truth from?
Oh, because you split the data. Look here. You split the data into 2 parts.
These but it's the same data, right? You just split it into 2 random sets.
Yeah, you split it into X train, Y train, and X test, Y test, right? You build a model on the training data. Are we together? Then you take the model and say, make a prediction on X test. So it will come up with Y hat or the predicted value, Y predicted. But you also happen to have Y test next to you. And you can compare the prediction to the Y test, which is the ground truth.
No, I think I'm very confused right now.
Okay,
I mean, it's not the predictions. So let's say you predicted whether it's a grape and it turned out to be a blueberry. Where did you get that information from that you're wrong?
I'll just, let me draw it.
I don't want to take too much time, but
this is important.
I think I'm missing it.
So see, here is the data set. Data. The first thing you do, step 1, you separate out the X from the Y. The target variable. Here Y is T, and here X is X1, X2. This is step 1.
Wait. Y is the target?
Y is the target variable. T. In our case, it's T. T for target. Right? It was that your job is to predict Y. Job is to make a model that can predict T. In this case, Y. It is convention to always represent, when you are writing code, the target variable as Y. It is the T column in data because your data comes as X1, X2, T. Right? Oh,
maybe I thought X is blueberry and Y is grape.
No, Y doesn't exist in the data. So you have to infer. I told you that, remember that in this, the Y is called T in the data, right? So you split it out.
Okay.
Right. And now what is your job? So now you do this data. Now you split X into X train, Y into Y train. This is your training data. You also have X test, Y test. In other words, Y being the T. In this particular case, it's T. Here also it's T. Yeah, it's the T column. You separated it out. You now build a model You build a model which works for training data, learns from training data, right?
Yeah, I mean, I get this part. It's not the explanation that is a problem. It's like, so T indicates whether you are right or wrong. What does T indicate?
Wait a minute, right? See,
So-
this is the ground truth, right? When you look at the test data, you know that for each of the X, this is the real ground truth, right? Let us call Y, if you look into the file, the values are 0 and 1. So in our mind, we can call this blueberry to help us. And this is the berry. We can imagine that this is the grape. This is our imagination imposed upon the data. Now this is making some prediction. I passed it X test. What will come out? Y prediction. It will make some prediction on the test data. But what do I compare Y predict to? For each value of X, I happen to already know the Y. So I can just put Y predict here. Actually, let me mark it as Y hat. Right? Predictions, as I said, a Y hat. So you would agree that for the test data, I can make a 3-column data set now. X is X, I already know, this is X. Y already know, Y test. I'm not writing test as a subscript. And then this is the prediction. Where did you get the prediction from? From here, from your machine. You got that, Raj? No? You use the machine to make prediction on X test.
Yeah, I got that part.
So now what you need to do is compare the Y pred with this. So suppose it says 0, right? It was supposed to be a blueberry and you predicted 0. Here it was supposed to be a grape and you predicted it as blueberry. So this one was right, this was a mistake.
Oh, so the third column, that T is the column which says, okay, now I understand.
Now you got it. So T is the ground truth.
Okay, so 1 and 0 is the same as blueberry and grape, or right or wrong.
You're right.
Okay.
Blueberry and grape.
Yeah, so you predict it and then you compare it with the actual T that was in the column, and then see how close you are. And okay, understood.
That is why you notice that model diagnostic, if you notice this line, element number 8, it starts with the entire confusion matrix is built out of comparing the Y test, which is the ground truth, with the Y prediction, isn't it? You're comparing the ground truth.
Understood now. The whole picture is clear. Yeah, thanks.
And everything follows from that, because this is the ground truth. Everything follows from that. Right? So guys, anything else anybody needs explanation? So you can divide the feature space or color the feature space by the probability that it is a grape. Okay? And now, suppose you want to build, you want to color the whole space. So, for each point, each actual data point, you said how confident you were that it is a blueberry or grape, right? These were the actual data points. But this entire space has a lot of empty space. Any one place you should be able to make a prediction. So when you fill the entire feature space with predictions, it becomes this beautiful graph where you can literally see how your classifier is acting. And you can also see where it is making mistakes. Do you notice that the further away you are from the decision boundary, the more deep colored it becomes? The bottom left is deep blue, top right is dark red, isn't it? So for classifiers, I would very much encourage you, especially when you're looking at lower dimension spaces, very much encourage you to make this plot. Many of these plots actually, once again, I must say, people don't take the trouble to do it. I mean, many textbooks don't even mention it very well, but make it a habit to draw these plots to see what is your model trying to tell you. Are we together? So if you got this one right, and then the ROC curve, if you just want to draw the ROC curve, you can say it is very good. And by the way, if you want to draw the decision boundary as a straight line, This is somebody asked me to do that. We don't often do that. Well, here it is. Here is the prediction decision boundary. Do you think the decision boundary is doing a good job? Yeah, this is it. And by the way, the reason I mentioned it is I wanted to show you this little bit of visualization code. I won't go into it because it's self-explanatory. Do you notice that I put an annotation here, decision boundary? So Matplotlib gives you the ability to annotate, it gives you the ability to do all sorts of cute things with your visualization. But this was just a question. Now, because it's a linear decision boundary, the other algorithm I could have tried is linear discriminant analysis. Isn't it, guys? LDA. We learned about it. Now, this part is easy. If you try LDA, the code remains exactly the same. The only change is you change the name of the algorithm. Do you see this? Instead of calling it logistic regression, you're calling it linear discriminant analysis. That's one of the beautiful things about scikit-learn. It's a very consistent library. When you use this, oh, did you notice the error? In fact, it tends to do a little bit better than the old one, but it might be fluke or it might be genuinely better. It's just a little bit better in accuracy, 1% better, right? Which may or may not be a fluke. Once again, you can do the same analysis, compute the y hat for the predictions. You can do the ROC curve. Once again, would you call the ROC curve a good curve? One would, right? And you can do, again, for each of the points that are actually there, you can ask, what would you predict it to be? And you can see what it is predicting it to be. And then, once again, you can project it onto you can draw the LDA decision boundary, probability map, and so forth. And you can, once again, draw the decision boundary, LDA decision boundary. And this is the decision boundary it is. So nothing too different. Right? The feature space, etc. So this is for the classifier data one. Let's take a 10-minute break, and then all of this code is there on your website, guys, class portal. In fact, I've released a lot of notebooks by now. Dozens of notebooks, 20, 25 notebooks have been released. Please take time to study it, practice it, become very familiar with it. I would. Now let's move on to the second data set. You'll notice that our pattern of analysis, the steps we'll follow will remain exactly the same. And this is one of the things you should do. Practice more and more and have the same set of steps. And then at each step, ask, what am I seeing? Right? What is it that we are seeing here? So with that, I load the data, do exactly the same thing as before. And then when I come here, how many classes do I see? There are 4 different classes, isn't it? T, the values of T, there are 4 different values. So can I use logistic regression directly? Well, it turns out you can, but the way it does it is that it does one versus the rest, and so on and so forth. So it does internally multiple logistic regression models. But the LDA is far more efficient because you can still find the center of these hills and draw perpendicular bisectors. I hope I'm making sense. Even if there are many areas of data, like here, this is one area of data, this is another, this is another, this is another. What can I do? I can connect the centers and find the perpendicular bisector. Isn't it? And I can have this for this entire region for A, this entire region for B, this entire region for C, and this entire region for C, this entire region for D. Isn't it? I can partition the space accordingly, right? And of course, outsiders. So forth. I hope I'm making sense, guys, that you can always use the LDA method for even if you have n classes. It's very natural. And Do you notice that how data does show a normal distribution along each of the axes? That should be encouraging. It means we can use LDA. Right? And let's try logistic regression, which, by the way, remember you said that logistic regression just draws one line between two classes. Well, the trick is you can say, suppose you have cows, ducks, and dogs. You can ask this question, is it a duck or not? Do one classification. So it's called one versus list. Is it a dog or not? Or is it a cow or not? And then you can build those decision boundaries and basically do the same thing. Come up with situations where it's more likely to be a dog rather than not a dog that region belongs to or has the highest probability of being a dog. Then it is dog territory, otherwise duck territory, otherwise. Yeah. So you can apply logistic regression. But the way it does it is internally it does multiple logistic regression models. When you do that, it comes with an accuracy of 97%, and it comes up with an F1 score of basically a pretty good F1 score, 97% F1 score, and it's doing pretty well. It's doing pretty well. Now, which you would imagine, if you notice, in your mind's eye, can you see that these things are reasonably well separated out? Would you agree, guys? Looking at the data? If you look at this data, they are pretty well separated out. So by now, the process is exactly the same. And you must be saying that, yes, I am pretty familiar with it. This looks good. Let me zoom into this picture a little bit more. You can see both of these variables seem equally important. This is your confusion matrix, true predicted class and not. But obviously, there are four classes. So where is one class being mixed up with the other? Are all the errors? The correct predictions are the diagonals. Look at the ROC curve. If you have to squint to find it, where is that ROC curve? Do you see it's right at the very top, isn't it? The area under the ROC curve is practically 1. It is, you can't even see it rise and reach this line. Guys, are we seeing that? So area under ROC curve is practically 1. Means this data was very easy to classify. Right? And when you make the predictions, it seems to make the right predictions. Let's, oh, y-intercept, something is, I'll have to rerun this code. I'll fix it and post it, or maybe on the class websites. So when you do, and by the way, you can use logistic regression, you can use LDA, right? When you do that, ROC curve is practically here. Well, this was easy. You could use LDA, you could use logistic regression, either of the two. Let's go to classifier 3, which is a little bit more complicated. You look at this. Can you imagine, this is a 2-class classifier. Can you imagine a straight decision boundary, a logistic regression decision boundary that will solve this?
It's an elliptical.
Yeah. So neither a logistic regression directly will do it, nor an LDA will do it. What will do it? A QDA, quadratic discriminant analysis, right? So if you just naively try logistic regression, you will get a pretty bad. You look at this. This is what you call a bad ROC curve, right? Isn't it? Guys, can you see it? The ROC value is actually worse than random. Make it because diagonal is here. And this deep red line, it is actually underperforming the diagonal by just a little bit. It's pretty terrible. And when you visualize the predictions on the model, it has nothing to do with it. You know, it just drew a straight line through the data. But what is it really? What should it have been? It should have been here. It's not doing a good job. So what you do is what could you do with this? If you draw a decision boundary, actually in the feature space, I need to run this notebook, guys. This is a script thing. If you try an LDA, you wouldn't go any further unless you do one thing, confusion matrix. You have to do a quadratic discriminant, by the way, the topic. So this notebook, guys, I need to fix it. There's a mix-up. I am doing quadratic discriminant analysis, but I'm giving the title linear discriminant analysis. Quadratic discriminant analysis, would you expect it to work, guys? You would, and you see it's doing famously. Look at the ROC curve here compared to the hopeless curve you saw with logistic regression. Right? So for this data set, because of the non-linearity, and look at this, how beautifully it makes the prediction map correctly. And this is it. It just gets it right. So, and it has a beautiful area under ROC curve. So now comes the question. I'll ask you this puzzle. Can you make logistic regression work? Hint, I taught you a trick for regression. How do you make the logistic classifier work? Because you know that the decision boundary is elliptical, isn't it? How do you do that?
X square by a square plus y square by b square equal to 1.
No. What have I, like, what do I do?
You multiply with some like factor like log or something that equals to that.
Yeah, see, I taught you polynomial regression. Remember, you can expand the feature space. Do you remember, guys? So what happens? Ellipse is a quadratic curve. So what is the minimum degree of polynomial I need to go to create an elliptical curve? 2. Right? So let's see what happens. What happens if you take this logistic, and in this particular case, I did it for polynomial features of degree 4. You can play with it, what works. Or try with 2, see how well it works, and see it begins to work, and then try better. And when you do that, lo and behold, logistic regression, which was a disaster, all of a sudden, is it working now?
Yes, too good to be true.
It's looking very good. In fact, it's working better than anything else. And this is the thing, and look at the prediction map. It's doing a very, very good job. What is the F1 score? I think it beats the other ones. 90, yeah, class probabilities. Yeah, no, it's more or less the same, 93%. How much was it for the other ones? I forgot, 93%. Quadratic was giving, what was quadratics? 93, it's the same. So they pretty much they compete and they have the same model, very similar models there for the decision boundary. So guys, there's a lesson here. The lesson here is linear methods, especially with polynomial expansion, can do a great job sometimes. Right? Now, people, and this is one of the typical interview questions you ask people. Rarely do I get a candidate. There'll be people who claim 10 years of experience in data science, etc. I give them a classification problem like this, and I ask, they will try it with logistic, then they won't do it, and they'll immediately jump to some highly nonlinear, like random forest or XGBoost or intelligence. Those solve it, but you lose interpretability. A logistic regression model is very interpretable. You have the beta coefficients, isn't it? So try to make simpler methods work. Don't immediately jump to a black box, because black boxes have an interpretability problem, right? They are opaque. And if you put in effort, if you put in thoughts, you can make your linear methods stretch out and solve the problem quite often, more often than you would think. So that is the lesson to learn. Now, you may say, this is all very good. We are building our muscles. Now let's do some real data set. So for real data set, we'll take the breast cancer data. Let me see if I have opened it. Okay. So this is the famous Wisconsin breast cancer data set. This is old now. Obviously, this belongs to 30 years ago, I believe. It was taken. At which time it was a remarkable research paper that mentioned this, and the scientists who produced this, they got considerable notice for this. So what they did is they painstakingly looked at cells, and they extracted features from it. They looked at the area of the cell, the smoothness of the cell, whether it is bulging in or out, right? The fractal dimensions. So they really went as a scientist and created all sorts of features out of it. They looked at the mean radius, texture, then they looked at the standard error of the texture, like how much variation there is. Basically, think of it as variance. They looked at the worst radius, the smallest, I suppose, and so on and so forth. And with all of these features, you can do, in our case, we can do description. So the whole problem in those days is, and even today is that, see, this is a scare. If you are a woman, people dread it. Right? I am told that some famous actress, actually, she had a high hereditary risk of developing the cancer. And so she preemptively had a breast removed. Is that scary? And it turned out to be a good decision. So it's like prostate cancer. Men are scared of prostate cancer. So women are scared of breast cancer. Now, how would you find that? X-ray may show something. You do an X-ray and there is some area, the fuzzy area. And now you're worried. Your screening test showed there may be something there. There's a suspicion of cancer. How would you know whether there's a malignancy or it is just a fat nodule or some dense area of the tissue, of the gland? So the way you have to do it is, you can of course open it up, cut open and go in there, take the tissue, put it under the microscope and then say, aha, we are totally healthy. But that is pretty invasive and it leaves a scar, isn't it? And it's traumatic. So one of the things that has evolved is something called fine needle aspiration. Fine needle aspiration is you take a thin needle, you poke it in deep enough to the tissue, and then you aspirate or suck out a little bit of the tissue. When you do fine needle aspiration, you have complete tissue. Now you can look at it under the microscope. When you looked at it under the microscope, it turned out that the human error rate was pretty high. Right? The lab people, they could not clearly tell whether they are seeing cancer or not. So then people tried this machine learning exercise that can you do it? And right off the bat, it came out with a much higher accuracy than people were getting by just putting it in the microscope and looking at it, from what I understand. And then, of course, the biological techniques itself, this is just a screening test. If you have a suspicion, then they are much more sensitive tests, which are much better than the machine learning tests, the biochemical tests that can be done. But as a first line, they tried to build a model using this. So there are lots of predictors. One of the first things you notice is when you have lots of predictors, you can do what? Correlation between the predictors. You can look for missing values. First of all, are there any missing values? There are no missing values. You can check for data imbalance. When you do this, you realize that there are more people who have benign, like whose tissue turned out benign, or the nodule just turned out to be a benign tissue, and about 200 odd people who turn out to have cancer, malignancy. Right? That is the ground truth. Right? So what would your baseline classifier, what would your dummy classifier do? If you ask your dummy classifier to predict, what should it predict? 50%.
That it's benign.
It's all benign, right? And so how often will it be wrong? So it's 357 over the total will give you 63.4% time it will be right, and the converse of it will be wrong, 36 or so percent it will be wrong. Right? 36 and change. When you have data which has so many features, data visualization, getting a sense of each of the features distribution helps. So let's look at the violin distribution here. When you look at the violin distribution, can you look at any one of these, a radius, mean? Tell me, which one can I use if you were to guess, which would be a good predictor that you could use perhaps single-handedly to make a reasonably good prediction? I'll decrease the size of this or increase it, right? So let's look at this. Can I use this one, radius mean? What if I did a decision boundary at value something like 14? At this point, if I make a vertical line, I mean a decision boundary that says if your mean radius is less than 14 or 13, right? It is benign. If it is more than that, it is valid. Would that work? It would probably work.
Most of the time, yeah.
Most of the time it would work. But texture is hard because there's overlap. You see the overlap region there. So radius mean is a pretty good candidate. What about perimeter mean? That also seems to be a fairly good candidate, somewhere around 90 if you pick a value as a decision boundary, that one single predictor might be pretty good, right? And you can find a lot of single predictors here that could be used. Yeah. And by the way, the fact that today, when you look at it as a box and whisker plot, and you can literally see, you can find good guesses of what would work as single predictors, right? It's a remarkable thing. Like, for example, you look at concavity mean, these two are fairly well separated out on concave points mean, right? So you could actually make a single variable regression model and get quite a bit of accuracy from that, though, of course, including all the factors we have. Right? This was a point actually made by a person who wrote a very controversial paper, a Professor Holt from New Zealand, from the bottom of the earth. Right? He pointed out that for breast cancer, including the original researchers, people were making very complicated models using all of these features. Right? But is that all necessary? What if you took only one predictor? He called it the one rule, right? A one predictor rule. And if you use only one predictor, then writing a classifier is as simple as just finding along that predictor the best point at which that point is the decision boundary, isn't it? Anything to the left is one thing, anything to the right is another, isn't it? Right? Am I making sense? Like, for example, for perimeter burst, if I take if I just split it at 110, right? Below that, it's all benign. Above that, it's all mean. I wouldn't be far off. It will make some mistakes, but it'll be a pretty good model. Right? And so he cautioned actually that people are in a hurry to build complicated models. And you shouldn't. Just as it is a good practice to first build a dummy classifier and know that a good classifier must beat the dummy classifier, in other words, 63.4% accuracy, it must do better than that. Before you go and do something very fancy, pull out the latest deep neural network, with something like that, why not try the 1 hour rule? Because it will tell you how obvious it is. The answer is obvious, right, in many ways. So he created the one rule thing. One rule thing we do in scikit-learn. It turns out scikit-learn doesn't have a support for it, but the best you can do is take a decision tree of depth 1. So actually, I wrote a little library that you can use, which I literally call the one predictor classifier. Okay. And it is there in our GitHub. I'll release it. And I'll put it in the course website. You can use it. So look at this. If you will notice that this is the point I'm making. The observant reader will notice that the diagnosis is oftentimes well separated by a single feature, such as radius mean. Look at that, or area mean, or something like that. Let us take this. You took area mean. When you draw out the box and whisker plot in great detail, you see how obvious it seems. One predictor will do pretty well. Many predictors may be better, but one predictor pretty much gets you quite far. Let's build a model with this. Why is this happening? First of all, you notice that if you do a correlation map, find the correlation between things, you notice that there is a significant degree of correlation between the features, isn't it? Deeper the color, the more the correlation.
As if is it because the area and perimeter is mostly dependent on radius itself, right? It's like 2 pi r and pi r square.
No, actually, that could be see, the human cell is very complicated. Those are, okay, so here's the reality. If you look at the cells, healthy cells are usually not round. They are like peculiar shaped, right? There could be banana shape, there could be any shape, right? So your pi r square won't work. But it turns out that the cancer cells, because the cells divide rapidly, what is, by definition, a cancer cell is a cell that has runaway replication, right? It is born before, it never gets a chance to grow to full size. It just replicates while it is still young and then replicates again. So what happens is it stays tiny. So you see a lot of tiny, lots of cells in cancer. Those cells tend to be generally more round than a full-grown healthy cell, right? So the area argument applies much more for the cancers, pi r square correlation. So if you were to filter this data and only take the malignant data, and there you look at the correlation between the radius and the area, it will be highly correlated. But it is not true for all the data. And this is where, real life is subtle. There are many nuances when you deal with real life. But it is true. So you see that very light color, and very light color is positive correlation. And there are lots of positive correlations here. And there are a lot of very, very dark colors are also very strong negative correlation. They are there. So you do expect a lot of that. And you can build a correlation chart. And when you build it, you'll see a lot of high numbers here. I'll let you meditate on it. You can do all sorts of pair plot for me. So suppose you take only the mean features, not the this. It's a smaller data set. Let's look at the pair plot here. What do you notice? This is just the diagnostic. You take only the mean. You see the distribution. If you just take two variables, right, and you plot it out as a scatter plot, you can pretty much see a decision boundary. Let me zoom in and show you. Some features, decision boundary is more obvious than others. Let me, where am I going? Look at this, the density plots. Look at this. Look at this. Can you guys see where my mouse is?
Yes.
You can see that one type of data is at the bottom left-hand corner. The rest of it is at other places. And in this, the two curves, this density curves, are fairly well separated out. So you can get a reasonably good classifier. Here it is even more true. See, the intersection area is a measure of errors. So if you were to take this predictor, it's hopeless because both of the bell curves are overlapping, isn't it? Do you see that both of the bell curves are overlapping? I mean, not bell curves, both of the density plots are overlapping. So you can't take this pair of features. I mean, this particular feature you can't take. But if you take, let's go through one by one. This could be used. This is bad because there's a lot of intersection. This is reasonably good. This is better. This is hopeless. This is okay. This looks pretty good. Oh, this looks even better, right? And this happens to be concave point mean, right? Concave point mean. So of all of this, concave point mean seems pretty good, isn't it? They have very little overlap. So the same thing for standard error, you can do that. And I won't go into that. Pair plot for worst, you can do. At the end of it, they all begin to look similar, but you can do a similar analysis. Now, so let's start building a model. First things first, you need to, what do we need to do? Real world data, we need to first scale it, right? You need to scale the data, right? And you can also drop some highly correlated columns. What are the highly correlated columns? You can figure out, hand pick a few columns and say, these are highly correlated. I'm going to drop it. Right? Label, apply, somewhere. Correlated columns, somewhere up there, I've defined, I've handpicked a few inside. They're too correlated, it's not used. So we make a dummy classifier out of these. With a dummy classifier, what is the average accuracy you are getting? 63%. That makes sense. Right? That is the ratio of good to bad, 63. You know that the benign cases are 63% of the data. So do you expect any better from the dummy classifier? No, you expect exactly the same result. So anything must beat, if it beats this, it's a good classifier, isn't it? Let's take only one predictor. We took area mean. And please play around with different ones that you learned and see what happens. When you take area mean, out of those many cases, you get very small number of errors, 9 plus 5. And what does it say? F1 score is 92% for 0, and for this 86%. So pretty good numbers, right? And average accuracy 90%. You think it is better than dummy classifier, guys? Is it a good classifier to use this?
Fairly good.
Pretty good.
50%.
And this was the point that Professor Holt was making, that sometimes you can get pretty good results with a very simple model. Don't get carried away by sophisticated model and the euphoria of using the latest and greatest tools. If you visualize once again how well, you look at the AU-ROC curve, it looks pretty good, isn't it? Guys? The area is 96%. So now let's do a multivariate logistic regression. We take all the variables, throwing away some highly correlated variables. Otherwise, you'll have multi-collinearity problems. When you do that, you jump to 97%. 97% is definitely better, isn't it? It's definitely better than 90. And so it is worth doing multi-factor this. But I'll tell you a trick. I deliberately didn't pick the best predictor. I'll let you discover which is the best predictor. When you do that, the hint is the gap between the best one predictor model and this predictor model will narrow down quite a bit. But I leave it to you to discover which is that predictor. So when you do a model with all the predictors, again, yellow brick comes in. It is telling you that the features that matter most are heavily, the big bars are a radius and this fractal dimension. Right? Fractal dimension again matters. Why? Well, it has to do with the biology. Human cells are irregular, so they have high fractal dimension. Right? So in other words, if you ask this question, right, what is the dimensionality? Given a circle, what is the dimensionality of the periphery of the circle? Given a disk, the periphery is a circle, right? And what is the dimensionality of a circle?
2.
Circle is 2 dimension, is 1 dimension, right? It's a curve.
Yeah,
Disk is 2 dimensions, circle is a curve. Right? It's just a line bent around. But it turns out that when you look at real life situations, like for example, if you were to walk along the edges of a snowflake, that you get into this beautiful, beautiful world of fractals. And then it turns out that it is no more, typically, you don't call it one dimensional. It develops a dimensionality between 1 and 2. So it develops a fractal dimension. So slightly, the more snowflake-like the boundaries are, for example, the example is given there. What is the actual shoreline length of England? You can argue that it's very, very long, right? Much longer than a rough measurement around the country. So that is where it is. It's the ratio of the actual length that you would see hypothetically and a very rough sense of it. That's one sort of an intuition of getting fractal dimension. So the fractal dimension of healthy cells can be pretty high, but that of cancerous cell is a nice one because they just bond. So it could be used, and this model is saying that is a pretty good predictor, not bad. So this is coming out with the feature importance. Now the feature importance, once again, because it's a linear model and you have scaled the data, quite literally you can read off the coefficients and tell which are the biggest coefficients in magnitude. So the biggest coefficients in magnitude that you can see are this guy, 96, isn't it? Number one, and this guy, 94, 0.94 and 0.96, feature importance. So according to it, if you plot it out, it says, oh goodness, I don't know why the dollar sign came about. I screwed up somewhere. Okay, where did I introduce the dollar sign? I'll remove that. This one also I'll fix. So these are not dollars, these are importances. Where's the feature importance? Percentage. Okay, I'll figure out where it's. So which is the most important feature? Radius. Second most important feature is this. And so on and so forth it goes. You can look up. Radius again happens to be the most important feature. Now in this model, we did not consider, yeah, fractal dimension is pretty close. It's an important feature, yeah. Right? Concavity is an important feature. Cancer cells are circular, like they're bulging out. So any banana shape or concavity is more indicative of a healthy grown-up cell. Same results you can get. So Shapley, remember I told you about the Nobel laureate Shapley, who got, he was in the Institute of Advanced Study. And by the way, have you guys seen the movie A Beautiful Mind? Anyone who remembers seeing the movie Beautiful Mind?
Yes.
Yeah, Russell Crowe.
Yes, John, and the about the life of John Nash. No.
It's about equilibrium, right? Play game theory.
Yeah, that's one. Game theoretic. So John Nash created the fundamental theory by which today, for example, wireless spectrums are auctioned and so forth. It said that in games, whenever people are negotiating, you can find points of Nash equilibrium. And ultimately, if both sides are rational, they'll gravitate towards the equilibrium points. And good negotiators instinctively know that how much they will get and not get. Right? So when skilled negotiators from both sides come together, they invariably end up at a point that you would call a Nash equilibrium. Right? And so anyway, so he wrote that theory. John Nash actually is a person that my generation used to actually had the pleasure of listening to the lectures of. So this Shapley was actually a classmate, a co-researcher with John Nash, and Shapley got the Nobel Prize for only one big idea, the Shapley values. So this is the Shapley value distribution of importance. Okay? What is the Shapley value? The bigger the Shapley value, the more it matters. Okay? So you can see radius has a huge impact. What is the other big Shapley values? Concavity mean is flying out. What other things are flying out? Compact SE is flying out in the negative directions. Fractal dimension is flying out in the negative direction. So these are the important ones. Then there is such a thing as partial dependency plot. It just shows how much, as you change the value of radius, the answer changes. Right? So the steeper it is, the more impactful it is. And clearly, this one, concavity mean and concave points mean pretty, like the answers are very sensitive to the values. Now, I have not explained about the partial dependency plot. I'll do it in a extra session sometime, so ignore this part. I will stop here today. We are almost out of time. But Shapley, learn to study the Shapley values. I give you a homework. Go study the library Shapley. I have used it here. I've also used it in regression. Make yourself familiar with it. This is the tip of the iceberg. I've just shown you one curve from Shapley. But there is far more in the Shapley library than I put here. Learn to use the Shapley libraries. Okay. Only for logistic regression, You can just read off the coefficients because it's a linear model. You can't do it for non-linear models. So guys, this is an example of a real world data set. You realize that all the techniques that you learned with classifier 1, 2, 3, simple data sets, they just transfer here. You build your muscle with simple data set, and then you grapple with complex data sets because you know how to grapple with it, right? How to deal with it. You have a particular intuition there. And this is it. This is your, this is a famous data set, the Wisconsin Diagnostic Breast Cancer Data Set. It has been quoted in innumerable papers. Anytime somebody comes up with a new classifier algorithm, it is almost a given that they will go classify the iris flowers data set in the this particular Wisconsin diagnostic data set. Okay? And there are a few other such classics. They are often quoted in papers. Let's see if you can do that. So guys, please study these notebooks. I have released all of these. If you don't study, don't practice, then you feel lost. I'm going to stop the recording.